Hello everyone, I welcome you all for the 7th session of the chapter Ray Optics. In our previous session, we derived a lens maker's formula, which is a very important one. So the lens maker's formula is 1 by f is equal to n21 minus 1 into 1 by r1 minus 1 by r2. So this is the lens maker's formula. So here n21 means the refractive index of the second medium with respect to the first medium. So if we consider a convex lens, so a convex lens is made up of glass. So this material is a glass. If somewhere here we have a focal length f of the lens, then if the refractive index of the glass medium is n2 and this medium is air, suppose this medium is air and the refractive index is n1. How do we write this focal length from the lens maker's formula now? This is 1 by f is equal to n21, refractive index of glass with respect to air. So this is written as n2 by n1 minus 1 into 1 by r1 minus 1 by r2. Here n1 is the refractive index of the air, which is equal to 1 always. So you can write this as 1 by f is equal to, if I write n2 is equal to n, refractive index of this glass, then this will be n minus 1 into 1 by r1 minus 1 by r2. So this term n21 refers to refractive index of the second medium with respect to the first medium, that is refractive index of the lens medium with respect to the outer medium. Okay, fine. So this is what we derived in the last class. In this class, first we need to see a thin lens formula. Okay, a thin lens formula. Yes. So what do we mean by a thin lens? First we need to understand what is a thin lens. So if you consider a convex lens, and this is a convex lens, and say this is an optical center, and if this is the thickness of the lens, okay, say for example the thickness of this lens is equal to some 2 centimeter. Okay. Now if the focal length of the lens is very large, and say for example here somewhere we have a focal length and this focal length f is equal to 20 centimeter. So here the focal length of the lens is large enough when we compare to the thickness of the lens, or this thickness may be even smaller. So it may be some 0.5 centimeter. Okay, it may be some 0.5 centimeter. So if the thickness of this lens is very small compared to its focal length, then this lens is called as a thin lens. Okay, if the thickness of the lens is negligible or negligibly small compared to the focal length of the lens, then that lens is called as a thin lens. So we have a formula for the focal length of the thin lens, which is given by 1 by f is equal to 1 by v minus 1 by u. So this is the thin lens formula, where this f is called as a focal length, f is the focal length, v is the image distance, this is image distance, and u is the object distance. Okay, this is object distance. Say for example here we have an object, and this is an object at a distance of u from the optical center, and say this is an image where the image is at a distance of v from the optical center, and here somewhere we have a focal length of the lens. So the relationship between focal length, image distance and the object distance is given by 1 by f is equal to 1 by v minus 1 by u. So this formula is called as a thin lens formula. Now let us see how does an image is going to form in case of lens when we have a linear object. Okay. In the previous derivation and also in this section, we considered the object to be a point object. Okay, it's a point object. The size is very small. Now we need to understand how does an image is going to form in case of a lens for a linear object. It is not a point object, it is a linear object. So let us understand this. First, let me consider for a convex lens. Okay, let we have an equiconvex lens. So what do you mean by an equiconvex lens? The radius of curvature of this surface and this surface is same. Okay, then we call that as a equiconvex lens. Let us draw a principal axis for this. This is a principal axis and somewhere here we have a optical center. Now let this point is the first focal point, okay, or focus. It's the first focus which is towards the right side of a lens. And let me say this is F1, which is the first focal point on the right side of the lens. Similarly, we have the focal point somewhere lies here. This is the focal point F2 for the lens in the left hand side. Now let me place a linear object which is behind this focus. A linear object behind this focus. For the formation of image in case of a convex lens for a linear object, we need to consider three incident rays, and after refraction, how do they follow? Okay, let us write the incident rays now. Let the first incident ray is this, which is incident parallel to the principal axis, correct? The ray which is incident parallel to the principal axis after refraction passes through the focus. Okay, so let me draw the refracted ray which is passing through the focus, and this ray is going to refract it in this way. Okay, next let me consider one more ray which is incident from the top of the object through the optical center. Let the ray is incident through the optical center, and this ray is passing without any deviation. So a ray is incident along the optical center and this ray is not going to deviate, it just passes along the optical center without deviation. Next we will consider one more incident ray. So that ray is incident along this focus, okay, along this focus, and this ray after refraction passes parallel to the principal axis. So let us write this. So this is the direction of the refracted ray which is incident along the focus. Now if you see at this point, what is happening? The three refracted rays from different directions are joining together. So at this point, the image of this object will be formed. So if you draw a line which is perpendicular to the principal axis, and this happens to be the image. Okay, what has happened here? This is the object which is placed behind this focus. The three rays are incident at the convex lens at the different directions. The first direction we considered is a ray which is incident parallel to the principal axis, and this ray after refraction passes through this focus and refracted like this. The second one is a ray which is incident through the optical center and which is passing undeviated, and the third ray is a ray which is incident through this focus and after refraction it is passing parallel to the principal axis. But if we consider the three refracted rays, this one and this one, all the refracted rays are joining at one common point. So at this intersection the image is going to form. So this is what the image of this object. So this happens in case of convex lens. Now let us understand what happens in the case of a concave lens. How does an image is going to form in a concave lens? So let us say that we have a concave lens. This is a concave lens. This is a concave lens, and for this concave lens let us draw a principal axis, and this is the aperture, and somewhere here we have a optical center. Let us write the focus F2 and F1 on either side and say we have an object somewhere here. Okay. First let me consider a ray which is incident parallel to the principal axis, and after refraction it will diverge, correct? So it will diverge. Next the ray is incident along the optical center which passes undeviated, correct? Which passes undeviated. Now if you observe the two refracted rays, so this is a ray which is incident parallel to the principal axis which diverges in this way, and a second ray which is incident along the optical center which is going like this. So if you observe these two refracted rays, they can never meet each other, correct? So they cannot meet on this side, correct? But let me trace back this refracted ray in the backward direction. So this refracted ray is appearing to coming from F2. Somewhere here the image is going to form. So this image is like this, okay? The two refracted rays are not actually intersecting. If I retrace this refracted ray in the backward direction, so we can meet at this point. So at this point an image is going to form. So you can observe the difference between this image and this image. This image is inverted image and this image is a erect image. Erect means which looks same as the object. Size may be different, but this image is as like a object. But this image is an inverted image and this image is formed due to the intersection of three refracted rays. But this image is not actually formed by the intersection of rays. We have traced it back this, correct? We have traced it back this. So an image which is formed due to the actual intersection of refracted rays, this type of images are called real images, okay? So this image is a real image, okay? This is a real image. And this image is not going to form due to the intersection of two refracted rays. So this ray is retraced back in order to get this image, correct? So that this type of image can be called as a virtual image, okay? This is a virtual image. So that is the basic difference between real image and a virtual image. A real image is the one which is obtained due to the actual intersection of the refracted rays, and a virtual image is not obtained because of the actual intersection. We have to trace back the refracted rays in order to get that image. So that is why this image is called as a virtual image. Fine. We are going to define a very important quantity which is called as a magnification, a linear magnification. What is that linear magnification? So this might be your 1 mark question, okay? So linear magnification is the ratio of height of the image to the height of the object. So it says about whether the image is an enlarged image or whether the image is a diminished image. So you can see here only, correct? So this image is, if you can see this image, so this image is almost similar to this, correct? So as you can see in this case, the image is a very small when we compare to the object. So this type of image is called as diminished images. And we may get an enlarged image in this case, okay? So a linear magnification says about the relative size or relative height of the image. Let us write the equation for linear magnification. So the magnification is given by, which is represented by m. So m is equal to hi by ho. So what is this hi by ho stands for? M is equal to hi by ho. Hi is the height of the image and ho is the height of the object. So a linear magnification is defined as it is the ratio of height of the image to the height of the object. M is equal to hi by ho. So it is not having any unit because so this is a height and this is also a height, therefore it is not having a dimension or unit. So a magnification is a unitless or dimensionless. So what is the significance of this linear magnification? Magnification is more than 1. If magnification is more than 1, that is height of the image is larger than the height of the object, the image is said to be a enlarged image. Next, if m is less than 1. If m has to be less than 1 means height of the image should be lesser than the height of the object. In that case, we get a diminished image like this, okay? Diminished image. So the image is diminished. So the last one is if m is equal to 1. So this is a very important case where the magnification is equal to 1. So if this ratio has to be 1, then height of the image and height of the object must be same, okay? So if the height of the image and the object both are same, then what happens is magnification becomes 1. This is the case where height of the image and the object becomes similar. What we have learned here? So how does an image is going to form in case of a convex lens and in case of a concave lens? And also we defined a very important term called linear magnification, which is given by the ratio of height of the image to the height of the object. So the equation says m is equal to hi by ho, and the significance of that magnification is this: if magnification is more than 1, then the image is enlarged image. If the magnification is less than 1, the image is a diminished image. And if magnification is equal to 1, then the image is having a same size as the object. So we have one more significance for this magnification. Magnification is negative for real images. Okay, magnification is negative for real images. Why we have to take magnification is negative for real images? See, m is equal to hi by ho. Hi is the height of the object. Since the real image is inverted image, from the sign conventions we need to take the distances below the principal axis to be negative, so we get magnification as negative for the case of real images. And the magnification is positive for the case of virtual images, correct? Because the height is above the principal axis. Here we should consider this height as positive because it is above the principal axis, correct? So I have forgot to say one more thing here. A magnification for a lens is also given by an equation V by U. Okay, magnification is also given by V by U. What is V? V is image distance and U is object distance. Okay, let's look out some of the common differences between a real image and a virtual image. Okay, the real images are always inverted images. Okay, so we'll get a real image which is always a inverted image. So the real images are always inverted, okay. And what about the virtual image? You can see here the virtual images are always erect, okay. Virtual images are always erect. Then the second point is that, so I said about the magnification, correct? So magnification is negative for real images and positive for virtual images. So for real images, magnification is negative, okay. For virtual images, magnification is positive, okay. Next, so this real image that can be captured on the screen because it is formed due to the actual intersection of the refracted rays. So real images that can be captured on the screen, they can be captured on the screen, but this will never happen in case of a virtual image, okay. So they cannot be captured, on the screen. The basic difference between the real image and virtual image is this. The first point says the real image is always inverted image and virtual image is always erect image. Real image is having a magnification as negative, and for virtual image the magnification is positive. Next, so these real images can be captured on the screen because it is obtained due to the actual intersection of the refracted rays. The virtual images cannot be caught on the screen because they are not formed because of the actual intersection. Now let us understand the next concept, which is a very important one, a power of a lens. So what do we mean by a power of a lens? A power of a lens is the ability of a lens to converge or diverge the incident beam of light. Suppose if you consider a convex lens, let me draw a principal axis and this is a optical center. Let a ray of light is incident at this convex lens and at this point it will be refracted towards the focus. Say this is a focus, therefore the distance from the optical center to the focus is a focal length f, and say this is delta, the angle made by the refracted ray with the principal axis is delta. Now this is f and this is nothing but the height of the object, correct? From the top of the object, a ray is incident means this becomes a height of the object. This is a height h. So here we have a right angle triangle. Say this is M. MOF is a right angled triangle. So from right angled triangle, MOF, okay, MOF. If I define tan delta, so this tan delta is equal to opposite side by adjacent side. Opposite side is MO, okay, this is MO divided by adjacent side is OF. So what is MO? MO is nothing but the height. So this is h divided by OF is nothing but a focal length f. So tan delta is equal to h by f. Now let the height to be 1 meter. Let we consider the height of this object. So this height to be equal to 1 meter. What happens now? Tan delta becomes equal to, h is equal to 1. So this will be 1 by f. So we get an equation like this. Tan delta is equal to 1 by f. This tan delta is what we called as a power of a lens. Okay. So power of a lens is represented by capital P, which is equal to 1 divided by f. So power of a lens is equal to 1 divided by focal length. Correct? 1 divided by focal length. So we define that power of a lens as the tangent of an angle, by which the lens converges the beam of light falling at unit distance from the optical center. Okay. So this is the definition for the power of a lens. So power of a lens is the tangent of an angle by which a lens converges the incident light or beam of light falling at a unit distance from the optical center. See, this is a delta. So tan delta of which the ray is going to converge falling at a unit distance from the optical center. So from O to M we have taken the distance as 1 meter. So that is why the definition is the tangent of an angle by which a lens converges the rays falling at a distance of 1 meter from the optical center. So this is called as a power of a lens. Or generally we can take a power of a lens is the reciprocal of the focal length. Okay. Power of a lens is the reciprocal of the focal length. And we write the SI unit of power of a lens is diopter. Okay, this is diopter. So the SI unit of power of a lens is diopter. So 1 diopter is equal to 1 meter inverse. The power of a lens is the ability of a lens to converge. How far it is converging or how near it is converging the incident light. So that is what we called as a power of a lens in case of a convex lens. For a case of a concave lens, what we have to define, a power of a lens is the ability of that lens to diverge the incident beam. Correct? So that is the definition for a power of a concave lens. The next concept is derivation, which is a combination of two thin lenses in contact. So let us derive that. The equivalent focal length of two thin lenses in contact. I have explained about the thin lens. If we have a thin lens like this, so for this thin lens, the focal length is somewhere here. So when an object is emitting the light and it converges the rays somewhere here, and we get an image at this point, correct? Now what happens if I combine one more lens to this? What happens to the image? So that is what we need to see here. Okay, yes. Let the two thin lenses which are combined together and they are placed like this. Okay, this is lens A and this is lens B. They have a common principal axis, and let f1 is the focal length of the first lens and f2 is the focal length of the second lens. Let an object O, which is emitting the light, and a ray of light is falling on the first lens. First lens forms an image somewhere here. Let me say this is an image V dash. Okay. So this is the image formed by the first lens. Say for example the second lens, lens B, is absent. Now in the presence of this lens, as the combined lenses, where does the image is going to form? So this refracted ray is incident on this lens so that it forms an image somewhere here. So this is the final image formed by the combination of lenses. Okay. This is the image formed by the first lens in the absence of the second lens, but this image is the image formed due to the combination of two lenses, correct? Say this as I dash, not a V dash, and this is I, the image I, and the distance for this is taken as V dash and for this it is taken as V. Okay, so V is the image distance for this image, which is a final image, and V dash is the image distance formed by the image of the first lens. Okay. See, in the absence of the second lens B, the lens A forms an image at this point at a distance of V dash. Let us write that. In the absence of lens B, the image I dash is formed at a distance of V dash. So by the thin lens formula, for the lens A. So object distance is U, image distance is V dash, and focal length is f1. So by the thin lens formula, what you can write is 1 by f1 is equal to, remember the thin lens formula, 1 by f is equal to 1 by V minus 1 by U. So 1 by f1 is equal to 1 by image distance. Image distance is V dash for the first lens. So this is V dash minus 1 by object distance. Object distance is this. This is U. Say this is equation number 1. Okay. Next. For the combination of lenses, I is the final image formed at a distance V. Okay. So in this case, what happens is this I dash acts as a virtual object. Okay. I dash is the image formed from the first lens. So for the combination, this I dash acts as a virtual object. So I dash acts as virtual object. Therefore, for the lens B, if you write a thin lens formula for the lens B, the object distance becomes this V dash, because I dash is acting as a virtual object. Therefore, V dash becomes a object distance for the lens B. Let us write that. For the lens B, this is 1 by f2. The focal length of the second lens is f2. This is equal to 1 by image distance. Image distance is V only, correct? Because the final image is V. Therefore, this will be 1 by V minus, this is the object distance V dash. This is 1 by V dash. Take this as equation number 2. Now, let me add the equation 1 and 2 to get the final expression. Adding 1 and 2. Adding 1 and 2. So if I add the left hand side, we will get 1 by f1 plus 1 by f2. Let us write that. 1 by f1 plus 1 by f2, that is equal to, the right hand side is 1 by v dash minus 1 by u plus 1 by v minus 1 by v dash. Let us write this. 1 by v dash minus 1 by u plus 1 by v minus 1 by v dash. So 1 by v dash minus 1 by v dash gets cancelled. So we get 1 by f1 is 1 by f1 plus 1 by f2 is equal to 1 by v minus 1 by u. I will write this first and this is second. 1 by v minus 1 by u. Take this as equation number 3. Okay. Now let us replace the two lenses by a single lens of equivalent focal length f. Okay. So we are replacing the two thin lenses in contact by a single lens of equivalent focal length f. Replacing the two thin lenses by a single lens of equivalent focal length f, equivalent focal length f. So this lens having a equivalent focal length of f at a distance of an object distance of u forms an image at somewhere here. This is v. So for this lens the equation will be 1 by f is equal to 1 by v minus 1 by u. I have used the same thin lens formula. 1 by f is equal to 1 by v minus 1 by u for this equivalent lens. So this is equation number 4. Now if you compare equation 3 and 4, this is equation 3 and this is equation 4. If you compare them, the right hand side of the equations looks like the same. So we can equate the LHS. So we get 1 by f is equal to 1 by f is equal to 1 by f1 plus 1 by f2, correct? 1 by f is equal to 1 by f1 plus 1 by f2. So if the two thin lenses of focal lengths f1 and f2 are combined together, the equivalent focal length becomes 1 by f is equal to 1 by f1 plus 1 by f2. So that is the equation. So if I write this in terms of a power of a lens, what we will get? See the same expression in terms of power, because 1 by focal length is a power. So the power of the combination of the lenses will be equal to 1 by f1 is the power of the first lens, 1 by f2 is the power of the second lens. So this becomes P1 plus P2, correct? In terms of power, we can write the equivalent power of a lens is equal to P1 plus P2. So if I have n number of lenses, then 1 by f becomes 1 by f1 plus 1 by f2 plus 1 by f3 up to 1 by fn. Well, so our eye is also behaving like a lens. So for that lens, the power may vary due to the several reasons. For example, short sight and long sights. So in order to cure those diseases, we are going to use this combination of lens. So our eye, if it develops a sight like a long sight or a short sight, so what a power of a lens is needed in order to combine with our eye lens, that will be decided by the equation power is equal to P1 plus P2. So this equation plays a very important role in curing the disorders of our eye. Well, so in this class we had learnt about the thin lens formula, what is magnification, and then we derived an expression for the equivalent focal length of two thin lenses in contact and also the power of a lens. In our next session, we will be learning about the refraction through a prism. Until then, thank you.